अपना टाइटल भी मैंने हिंदी में इसलिए बनाया है। सबसे पहले तो मैं धन्यवाद देना चाहूंगा निदेशक महोदय और शैक्षणिक प्रकोष्ठ के अध्यक्ष का कि मुझे यहाँ पर मौका दिया गया अपनी बात कहने का और काम को आपके साथ दिखाने के लिए। और मैं आज जो बताऊंगा आपको वो है कि बूंदे मीन्स इज नॉट पानी की बूंद, बादल की बूंद। बूंदों और वायु गलय पात्रों की गतिकी को समझने हेतु प्रत्यक्ष संख्यात्मक अनुरूपण। जैसे हिंदी में बोलते हैं प्रत्यक्ष को प्रमाण किया, बट ये जो प्रत्यक्ष है वो संख्यात्मक है, इसलिए उसको कुछ प्रमाण चाहिए रहते हैं। तो इसके प्रमाण के लिए हम लोग परीक्षण मतलब ऑब्जर्वेशन की चीजें से ऑब्जर्वेशन से इसको वो करते हैं, वैलिडेशन करते हैं। So actually somehow now I can switch into the English. So this is basically a video which is not working right now, and it was working on my PC. So I'm actually going to talk about the evolution of the droplets aerosol activation in a small domain. So it is basically all about the cloud turbulence. So I have the three part basically, which is droplet dynamics, aerosol dynamics, and turbulent property. I think I can cover only these. If there is some time, I will go tube convection. I kept it separate because it is separate domain. The DNS domain is different in this case. So, I mean, you all are expert here in the modeling part, and you know that how the clouds are important for the general circulation model. So we do the parameterization, and then we talk about the clouds. We have the different height of the clouds. I mean, high level and then middle level and the low level. So my work is basically related to the low level cloud, mainly the cumulus cloud, and how the microphysics happens at the small scale, or I will say smallest scale here in terms of the turbulence. So what is happening at the smallest scale? I just put it into a few bullet points here. So we can study the entrainment and the mixing of the cloud edges, which I showed in the previous figure, and how the droplet size spectra evolve. And recently people are talking about, can we validate the partial models using the DNS, which I have just started the things, because I mean, I heard from the people who are doing the large scale model, they say that most of the things we take from the partial model. If you are parameterizing, or some information we are taking from the partial model. So I mean, this is something new I'm starting to compare with the partial model. Second thing is the aerosol activation and their dynamics. So aerosol dynamics, I will say, it is a CCN activation, and once they activate, how the aerosol dynamics happens in a different environment condition, like chemical properties. Once it is the aerosol, means we have so many other things. Cloud droplets, we just talk about the water and all, but aerosol have many other things. And then some turbulent property. Since it is a cloud turbulence, so we also study the turbulent properties, like vortex dynamics and all. So I will try to cover this part also. So again, come back to the modeling part. So as I mean, I just put very roughly that generally we think about the large scale models have the three different parts: ocean, land surface, and the atmospheric. Atmospheric again has many parts. So I just focus on the two parts: atmospheric. Mainly, I will say one part of physics, that is the cloud dynamics inside the atmospheric physics. So in the cloud microphysics, we talk about, and the microphysics generally people are doing the large energy simulation. I also connected here with the atmospheric chemistry because we are also working on the aerosol. So aerosol has the chemistry, so I thought it may be connected to the atmospheric chemistry. But the small scale simulation, people are generally using the large eddy simulation and the direct numerical simulation. So I'm basically going to talk about these 3-4 things which I pointed out in the previous slide. Then why I put this figure here? People are saying that you are doing this very small thing. Where is the what is the connections? How you are going to connect the things? So that's what I said, that the connection can be from this way. We can go from DNS to LES if we can do it some kind of information passing from the DNS to LES. and then we can, improve and give some information to the large scale level. So I start with the droplet dynamics. So this is again a video. I don't know why it is not working. It should come automatically, but it doesn't work here. Okay. So in the droplet dynamics, first we talk about whether the droplet drops are existing. If they are existing, and how they will evolve, means what is the size spectra, whether it is moving left side or right side. And that size spectra, I think, is an important part for the any modeling. If you go to even the large scale, even in the LES, we have to give the size spectra initially in the different size spectra. So this is what all the discussion goes on, generally goes in the DNS part. Here, when we talk about the modeling, we have really a mathematical model. So this is the model which generally very standard model people use for the DNS. So the red part is the fluid flow. The fluid means the turbulence flow, which we are resolving on the grid point. And then we have the this velocity and the Q and the temperature. And then within the grid points, we have the particles, that is either aerosol or the droplets. So all the droplets, the particle movement, we have the Lagrangian equations. That means we are solving their velocity, the size, the positions, and also we are calculating the supersaturation. And these two are connected through this condensation rate. The condensation rate is calculated based on the number of the droplets available within a grid point. So this is the way we connect it. So I will not go into detail how we are solving and all, but here I am telling that it is all we are solving in a spectral Fourier space. This is pseudo spectral method. So everything we solve in the Fourier space, then bring it to the real space, then do these calculations, and all those things happening every time steps. It is second order scheme we have used.
Incompressible. Incompressible.
No, incompressible. Consider it's a very small thing, so we can take. So another thing is we are doing this turbulence in a box, is a small domain. So we took the periodic boundary conditions. So we call it, some people in turbulence people, they call it the box turbulence. And since this is a turbulence, so we have to give some initial condition. Boundary condition is all three direction is periodic boundary condition. So the initially we create the turbulence, and the turbulence we are providing any initial condition. So this is suppose the domain, and then we are providing the turbulence flow. So this is and we are creating a cloud slab. So this is a setup for the entrainment and mixing scenario. So if we want to study the mixing property, so there will be a warm air, there will be a cloud air, so there will be a mixing. If you start the simulation, so the mixing will happen, and then we study what kind of mixing. So this is the part like initial condition. Another thing comes the computation. So it is known as the very computationally expensive simulation. So suppose we want to do only, generally I am doing in a sub-meter domain. So I just consider here, suppose we want to do in a 1 meter cube domain, and we go up to the Kolmogorov scale. So the grid length went to the 1 millimeter. So in this case, we will have 1024 cube grid points. So this 1024 cube grid points, we are solving all the equations what I have showed, every grid points and then every droplets. So basically we have to do parallelly on a supercomputer, we cannot do on a PC, and we need to do the decomposition. So the whole data is decomposed in the 2D processor topology. So some of the models are like a to do the 1D processor topology, but here we have the 2D processor topology. So each processor get one particular pencil, we call it in the HPC language, is called the pencil. So that much data is available for the each grid. So this is the just an overview how we are doing the calculation and the computation. Now I will tell about some results. I will go back some 10 years before when we started this thing. And I think this is I'm giving the first lecture after I join here, but I will tell that 10 years before again I gave a lecture before my joining. So I am going to that back in 2012 when the code was we were developing this code, and once we develop the code, we actually need to validate some kind of either the observation or the theory. So here the first thing was that this is all the things I have done in like 25 centimeter domain, and we did the different kind of 12 different simulations with the 3 different radii, the droplet radii, and 4 different number density. We wanted to actually somehow validate with the theory. So one of the thing is the relaxation process. So the relaxation means when the mixing is getting relaxed. When we are talking about the mixing, so mixing the parameter for measuring this mixing is called the tau phase, the phase relaxation time. So we have a theoretical formula for the phase relaxation time. So we calculate this theory and theoretical formula, and we calculate the phase relaxation from our data, DNS data, and then we validate. So this is the first validation we did long back in 2012. And second study we did the mixing type of the mixing, basically, or what is the extreme case of the mixing. So mixing in the cloud with mixing we defined in the 2 types, mainly 2 categories, either the homogeneous or the inhomogeneous. If it is extreme cases is the homogeneous or inhomogeneous, or it is a well mixed. So how to calculate, how to study or investigate these extreme cases within a tiny domain? Normally in the cloud we have everything. The cloud range is very big. We cannot do in a small the box things. So what we did, if we go for this the rate, the growth rate, there is a growth constant. So if it is a normal growth, this is the case, like normal growth, it is mixing is happening, the droplets are growing. But if the growth is slow, so that means the droplets are growing, condensation is happening small, and evaporation is happening fast. If you remember the initial condition what we are providing, there is a warm air and some drop. It's already here. So this is the warm air, and this is the warm air. This is the cloudy slab. I put different. This is basically animation. It's not working. So these blue colored droplets, they are basically inside the cloud slab. They get more supersaturation. They grow. That's why I put in the blue color, means more water is there. And all this border one, they will first get exposed with the warm air. So they are expected to, go faster, or completely evaporation will happen. If that is the case, then we will see this kind of size distribution, means this is more on the left side. So some complete evaporation will be seen. On the other hand, if it is a homogeneous mixing, the extreme case of the homogeneous, that means the condensation is happening faster than the evaporation. So in that case, theoretically we see that this is the size distribution. Will say the whole spectra will shift towards the left side. If it is because all together they are going down. It's not like some of them is getting evaporated, some of them is getting condensed. So everything, the whole spectra gets shifted. It is the overall things. So if this animation was, I could have shown you that if we run this for a few seconds, all this green and the orange current droplets, they evaporated completely. They will die out from this domain. They will disappear. Only the blue one will left, because blue one is in the cloud slab, and they actually get more supersaturation. I will not spend much time because I have so many things to tell. And this work is already, put into the NJP, New Journal of Physics. After these kind of validation, we actually, I will say that everything, all these things I have done using the constant temperature. We consider there is a constant temperature, and we did the study. But we have to do full real simulation. So we included now the in our Numerical equation, we included the temperature equation. Now the first thing is when anytime we are changing in the model, any model, we have to validate. So first thing is to validate all those simulations which we did in the constant temperature, and see what is the importance of the temperature, how the temperature is changing the droplet size. So this paper is actually in the JAS in 2014, and there are many results. I just put one result here. The main thing here we are saying, we did the series of the simulation, but we changed the turbulence condition. The D case is called the decaying. So initially we provided the turbulence, then we are saying, okay, let the droplet consume this turbulence, let it die, because dissipation will happen. So it is decaying, and this here we are keeping the force, so it is sustaining. So you see that when the small droplets are there, there will be some complete evaporation because they are small. There is a mixing is happening. Some complete evaporation will happen. But think about the 20 micron. This is a border size when the radius is 20 micron. After that, the collision and all take place. But this is the size where still we say that the evolution or the growth happens only condensation and evaporation. In this case, you see there is a complete evaporation when the turbulence is not present. In the decaying case, we can see some kind of complete evaporation at the time of 30 seconds. But when the turbulence is present all the time, then we don't see any complete evaporation. Even the size spectra is going into each other. That means we have got a well mixed condition. So this is the role of turbulence and the temperature, including in the whole equation. So after that, I mean, up to the 2014, the development of the model and all was going. Now we say that this is the fully model we have. Now, what is the next step to validate with the observation? So first thing I did, we started validating with first thing is the observation. So we took the data from the KIPEX flight and we give as a size spectra, initially polydisper size spectra given to the DNS, and then we compared it. So these are the size flight number and all. Research flight 45. The size spectra we provided is all provided by Sudarshan. Dr. Sudarshan is sitting here. So we gave this size initially, and then we run the DNS, and then we comparing back again the observation which has happened after few seconds, few seconds or few minutes, whatever. So the time is written here, and basically it's very difficult, and it's really people cannot think how you are comparing a small your box simulation with the big flight thing. So what we did here, we actually created a small box and we scanned through. So we basically created a flight inside the DNS domain. So the way we are taking the flight observation in KIPEC, the same way we did inside the DNS domain. So one, I think it is 1 centimeter cube, 10 centimeter cube. I don't remember exact. Maybe this work, the analysis was done by Sudarshan. He put in his thesis also. So we just did the same thing, and then we are comparing many things: the size spectra, and then the mean radii, and the number density. See, we can see some fluctuation in the number density, but other things are matching. So this is what we can talk about, that in the DNS, we can see each and every droplets and the nearby fluctuations we can see, which is not, I mean, possible in the large scale domain models and all. So
the other this thing, so here the x-axis is time, right? Their x-axis is centimeter.
Yeah, so when the flight is going, if you see the time, actually it is moving from some direction, you know? So it is moving from this place to this place. The same way we actually put one
cube. This time, when the flight has moved, is it the same distance what you are writing in x-axis?
That's what we calculated, yes. That's what we calculated from the flight data. And the second thing we did, how the turbulence is basically behaving when we talk about the domain. Actually, I always said that DNS is very small domain. People say that how the domain is changing. So this study is done. It is in the published in JFL. So here we concluded that the strength of the turbulence basically depends on the domain size, and the range of the scale is also an important parameter. And again, I am saying that there are many things: size distribution, saturation. These all depends on the domain size. So basically, you see the setup here was that here we took a little bit bigger x-axis, and y and z was so 1 meter cube, 1 meter, and the x was the 2 meter cube. So we just wanted to see how the size is affecting the overall turbulence properties, and this. As I concluded before that, what are the main points? And this work is really very became famous, or I say the journal people have put into the front page when it was published. Some of the figures took it from our study and they put on the front page. So here I wrote that the domain size important. Now this is the key point. If the domain size important, why don't you do the study of the domain? Okay, the domain of the DNS what we are talking about. So the next study we did. The next study was basically to see the scale dependent, the physical scale, the computational domain scale, how it is changing the cloud microphysical properties. In the JFM paper, we have seen that how the turbulence properties and all there are a lot of results in that paper, you can see. So here we wanted to check that what is the cloud microphysics properties are changing with the size. So one thing is the mixing, if we take the same environment condition, a small domain, bigger domain, bigger domain, bigger domain. First thing is that the mixing property changing. It becomes more inhomogeneous kind of mixing. And the shape and droplet size, I will go to here, then I can explain better. So this is a small domain, 12 centimeter, 25 centimeter, half a meter, 1 meter, 2 meter. You see, everything is same, but the size spectra at the maybe we can see at the end of the simulation, this black line, it is basically shifting this way into the left side. So the tail is going to the left side. So the tail left side is indicating the inhomogeneous mixing. So the conclusion here, one of the conclusions saying that when the size is increasing within the same conditions with the same number density, the mixing is changing into the inhomogeneous side. And then we did more, when we saw that this is happening, we did more study, some different microphysical parameters. So like if you see the size, cloud size, relative dispersion with respect to QL, with respect to Dame Kohler number, all these parametric study we did, and we always find that the size is matter. Size does matter, I will say. So from this 2017 and 18, this study, we just came to know size matter. Now the question comes, how big DNS we can do? It is very expensive, no? So how big? This question I even asked when there was a DNS conference here in 2018. I asked all these people who are across the world. So whatever the size you go, there is a limit how much computational power we have, how much big domain we can do it, but still it is a small domain. No? And why we want to do that? Our idea was that it's still the same, that how you are going to provide the information from DNS to our weather forecasting things or some I mean kind of operational things or I mean the large scale model. So this question still lies in how big we can do. So for the how big things, the question remains that okay, can we do something which we can provide the LES information? So first thing is in the LES, what is the grid size? Can we provide some information from the whole DNS domain to one LES grid? So this is just a conceptual input. Can we run the LES in a high resolution up to the 5 meter? I don't know whether it is possible. People are running here DNS, WRF and the PALM LES people are running. So how, suppose it is possible, we can go to the 5 meter. Can we run the DNS for the 4 meter or 5 meter? So that we can provide some information, maybe the mixing diagram or maybe some 3KE, whatever is required at different grid. That is the concept people told, and the people who are developing the LES. But think about 4 meter cube. If we talk about the speed, again the Kolmogorov length, 1 millimeter cube, 4096 cube grid cells. Each grid cell will be solving all those partial differential equations, Navier-Stokes equations. 3.46 billion droplets. So all those 7 equations at the billion, we cannot do. Anyway, we actually tried. Initially, we tried running just. I started running this one, and I thought maybe the initial condition will be generated. It happened. Some one file generated in maybe in a month time or something. The size was 2.7 terabyte. So it is. We concluded no. It is. Suppose even somehow in the word there we have the space or something. Another question is that big size. If you start reading, when this file was written, we actually noted on the time it was 4 hours to writing. When you read it again for the reading the initial condition, it will take again 4 hours. So first research we thought how we can do that time the new computer came. So we actually worked how we can optimize the parallel I/O. We are using thousands of the cores. So can we optimize? So this research we have done actually in the system level. So now this everything is in the, we have put in the scripts, whatever the script you are using, that script already user support have put. But that worked well, and we did the parallel optimization. This work is already published in the lecture notes of computer science in this Springer, and that 44 hours time came down to 45 minutes. So that was a significant reduce in the time, but still it's a so big space we cannot do.
That space is deleted, no?
Immediately we have to delete. We have no space. Immediately we have to delete. That's IO, whatever the available in the routines, we all tried it. But this is the system level commands, how the operating system is behaving, that we change. So that we can, I mean, many other things in the next study, you see that I have done a lot of study that how we can project. If I want to tell to the people here, to the IIM that I want to run it, so I have to project. Okay, I want to do the 2 meter cube. How much time it will take? So I calculated if I use the 1024 cores, I want to go up to the 2 meter cube. So you see the time, it will take 80 days. We don't have this, computational time that much. 80 days is not free. Nobody can run it. So this is the work actually.
This you're doing on the geographic GPU-based system?
No, this is all running on the CPU. This all code in the pure code run.
The GPU system.
GPU code we have to develop actually. People are trying to. I think some GPU code has come up in the NCAR with this Lulin and so has done, but they told. But I never saw any result from no publication and no other news. They told me that they have developed. Or so actually the code is very nicely scaled. If you see that up to the 1000 code we are getting the linear speed, even sometimes super linear speed up. So the code was very nicely optimized. If we projected, the projected time is going 80 days and all. So this is a lot of study I did, and this is after optimizing the memory level, after optimizing the operating system level. So all this study we have done, and this also published in the SPC journal, the parallel computing. So overall, what is the thing is that we cannot go to that bigger domain, which is required to give some information to the next level simulation, LES or maybe regional level. So then, what is the another thing? Computationally, we cannot do. So we can think the other way. So what we think that this is the domain we have tried this and that. So how we can do the simulation for the bigger cloud, but less computational resources, because computational resources we don't have.
We are doing no for long time parameterization. This people have been doing that for 50 years.
So we actually, did some kind of but we are not going to do any kind of parameterization. We are simply saying that we will still be up to the Kolmogorov scale. So how we can change some small one parameter here so that we can scale up the physical properties. So the idea was that we can find an approach similar to the real DNS. We will be using the same equations what we have done in the previously developed for the testing initial the benchmark code and work, and then we just calculate out these theoretical values. We say that if the viscosity change, then actually we can scale the things. So if the viscosity changes, then we can change the length, but we will have the same number of the computational grid. So this is what we are saying, that if we increase the domain size without changing the number of grid points, then actually we can say the scaled up DNS, but still it is a DNS. There is no other parameterization which we are doing. But the thing is that if you say anything, any change in the model, again the verification comes. So we have actually done this real DNS verification. First thing is this size spectra, the spectrum is energy spectrum, not sizes. Energy spectrum is where you're following the theory or not. The 5/3 slope is not. So if you see the real DNS, we have this slope. Scaled up DNS up to the 10 meter, we have this slope. So this is the spectrum. You see that this is the real DNS. We are going 10 times, 100 times, 1000 times. Just a study we did in the pure turbulence phase. There is no droplet right now. So you see that we are following the slope, but the spectra is shifting to the left side. Some wave numbers are losing. So we can have a trade-off that we should be near to the real DNS, and how we can go to the bigger domain. One thing is the turbulence properties theoretically. Second thing is this is the flow. But what about the droplets? If you are changing the domain, the droplets will also go into the power cube. No, it's a cubical domain. The number density will, yeah. Okay. Before that, I will say we have done a lot of theoretical verification for this work, and like the kinetic energy, what should be the mean value, how we are fluctuating from the mean value. So in this case, actually in the turbulence fluid flow case, everything is worked fine up to the 256 meter. Next question comes the droplets. 4 meter cube, we see the billions of droplets. If you want to go 10 meter cube, this is 10 to the power 11 droplets. We cannot solve 10 to the power 11 differential equations, or in one droplet 7 equations and all. So we have a concept which is called the super droplet, which was very valid concept given by the Shima in 2009, and that is very well defined. So we thought, why don't use this concept here in the real DNS? Okay, so we actually initially tested this real DNS thing and see whether anything we are losing any microphysical property, and we found that everything is same. So what is the concept here? That we will have the droplets same way, but each droplet must be representing a bunch of the droplets. So suppose there is a 10 micron droplet, we say this is one droplet, but this droplet is containing 1000 droplets. So and different droplet will have the different multiplicity. So this will define as what is the multiplicity or what is the size. At particular multiplicity, particular size, how many droplets one super droplet is representing. So this is a very valid, very proven concept by the Shima. So we have used in the real DNS, and then we did the whole simulation with the turbulence flow as well as the droplets. And you see that we did so many experiments. This is all the work by Louis Thomas, his PhD work.
This is similar to Arakawa's cloud function.
There is no function here.
Multiple types.
Multiple types may be cloud, but here we are seeing the
only one drop.
within the drop we have single mono size, one size only. So there is a R1 size. We say this droplet have the size of 15 micron, but 1000 droplets. So when we are actually calculating the mass and all those things, then this multiplicity comes in the picture. Otherwise, if it is everything same, we are solving this one equation for one super droplet. But when you want to see what is the condensation rate, how much the liquid water content, then you multiply that guy, M is there. Otherwise, everything is same. So the concept was very clear. So here we found what is the limitation. So the limitation is that if we go up to the 60 meter cube domain, so we go to 10 to the power 5 multiplicity. After that, it is fluctuating. This is the graph of the supersaturation fluctuation, standard deviation of supersaturation. So this we should not go away from the standard deviation. Here we are putting some restriction. Till now, whatever the study is, it is all PhD work by the Louis. So up to the 64 meter cube, and that is the this is the multiplicity we can go. After that we can go. So this is what the limit. Everywhere we are going in the simulation, what is the limit we have defined here. So all this study, all the investigation lead where? Come back to that meaning of the DNS, where is the contribution. So this is the real DNS. We were in the sub-meter thing. I have gone up to the 1 meter only. All those experiments going bigger is not possible because of the computational resources. Now we come up with this approach, scaled up DNS. This approach is basically whatever we have done. It is all published in the ACP. Okay. So now the next question comes: if we want to give any kind of information to LES grid, so we have to work from scaled up DNS to LES. So this is not done. So this is what I have put as a
scale am I equal 10,000 to 1,000, 1,000 to 100. Cannot be. So, and then you are going up to 1 millimeter. You have to also scale, you have to make it very, very small. Cannot be equally scaled.
Oh, okay. I mean, then it cannot be visual. I mean, that's why I'm writing the things. If we see 1 millimeter, nobody can see it here.
Because it looks
Proportion. You have to make proportion.
I mean, at least I can change here. It looks bigger.
Make it
But the
look
thing is that if I go from 10,000 to 10 meter, it will not be this way here. So I have to tell my word that this is the scale here. So this is the research problem which we can do next as a future. Domain alias we can run in the few kilometers. I mean, or into the 1 kilometer to the 10 kilometer. So depending how you are doing, what is the grid size and all. So some alias expert can tell.
5 minutes, huh?
Oh,
Yes.
I have the second part now.
Yeah. Finish it.
Vayu Bilay Patra now.
Yeah.
So aerosol activation and different environmental conditions. I will not go now into the theory. So the theory, maybe the expert knows what is the I mean the threshold supersaturation threshold, the size of the aerosol to become the CCM, and also different size has the different peak value of the supersaturation. So actually I was not knowing the time, so I put.
What is that?
So this is how we are going to implement into the DNS. So we have done DNS for the droplet. There is a droplet constant, but when it comes to the CCN growth, we have to change the equation. It becomes the extra part. This is the supersaturation of the droplet, which has this equation. Here we have the two different kind of radii. One is the dry radii, one is the wet radii. So dry means the pure aerosol when it is not condensed, and the wet means when it is getting condensed. So two types of the things. So we have implemented. But the question, if you remember, this Kohler curve is saying that you have to give continuous supersaturation, so it should reach to the peak and then become across that border to get activated. So how to provide that? So we have actually made the whole DNS as a rising parcel to provide the extra supersaturation continuously. So this is the way we did, and then if you see here, we have actually here the first time we have comparing with the parcel model and the DNS rising domain. So here we see that the parcel model, everything we consider as a average of the domain, average value. But in the DNS, we are taking about the fluctuations of values, fluctuations of the supersaturation, how the fluctuations is changing. So here we are seeing that it is just like this either coming or all of a sudden all activated. But in our case, there are some steps that how the fluctuation is behaving. So this is the one single salt simulation we have done, ammonium sulfate. In the ammonium sulfate, initially we are giving the at the below the cloud base height it's 0 meter. Slowly it goes up 90 meter. You see that some of the aerosol started activating, and then finally when they are activated completely, you see this is the activated part and this is the unactivated part. So whoever got across that Kohler curve, they got activated. So this is what in the theory we see in the Kohler curve. So we have simulated this in the DNS. So now this is just a single salt domain, but when we talk about the aerosol, there are many different environmental conditions, whether it's a pristine condition or polluted condition. The polluted condition, there will be more number density. So what will happen? In the pristine case, you see all these parameters we took. In the pristine case, after the activated, we are not finding very one or two particles which are unactivated case. And polluted case, there are many. After the activation process happens, there are many unactivated particles are available. So it is simply that the same domain, same supersaturation. When the more number of the aerosols available, they will eat up the supersaturation. So some of not getting enough supersaturation to get activated, so they became still there remains haze particle. So that is what we have got the same result in the DNS. And then like many other properties, the fluctuations of the supersaturation radii and all, we have studied what will happen in the pristine and polluted case. Another thing is we have done okay here. This is the part with single salt. then we consider that any aerosol in the nature, it is not a single salt. It can be a mixture of the organic and inorganic salts. This is what always when we see this HACCP things results is we have found that much organic. This is the part of the inorganic, the distribution comes. So we thought that we can give some kind of numerically distribution of the organic and inorganic. So starting from like 1 to 9 ratio of the inorganic to organic to inorganic. Organic is less, inorganic is bigger. So that's why the kappa value is higher. So inorganic means it is more affinity to absorb the water. So any inorganic will have the higher kappa value, organic will have the lower kappa value. Based on this table, we made the size distribution for the initial size distribution. Okay, here the Kohler curve I have to tell that whatever the Kohler curve we talk about, that is the standard Kohler curve with a single salt with a one particular different size. But one particular side, if the salt is changing, the kappa value changes, then the Kohler curve, the peak value changes, peak value of the supersaturation. So that is the main factor here. So we took the 4 different cases like pure inorganic, then mixture of the organic plus organic, then pure organic in the 2 different cases with different kappa value. What we can think about that? If it is a pure inorganic salt, it should get activated fast because it can take the water faster. It has the higher kappa value. Hygroscopicity is better. But in this experiment, we found that the mixture, this is getting activated first. So we still, have to think about that why it is happening. But after that, this color is coming, the inorganic color is coming. So pure inorganic should come here, but we are getting this mixture. So this is one, result we got in terms of the when we are actually putting.
Summarize the whole.
You go to your concluding part.
Okay. So the another study we have done is basically we are changing the vertical velocity. When the rising parcel is going up, we have actually changing different vertical velocity, and we are seeing that observing that how the activation portion, the aerosol activated, how they are changing. So we found that if it is a higher vertical velocity, we get the more activation things. So this is what we have to see whether it's validated with the other observation, but we have already done some validation with the 5-chamber experiment in the Michigan Tech. So now we are planning to take this HACCP observation. We are taking this distribution, and we are prepared some the experiment for DNS. So in this HACCP, they are having a CCN chamber where they are changing the supersaturation in the stepwise. So same kind of supersaturation input we have to provide. So this work is going on, and in the future I will try to take this Kypex observation also, because now Kypex observation is saying they have particle by particle information, so which we can compare with the DNS. So this is the part where I am talking about the aerosol and droplet dynamics we have done. Okay, and in the future we can go like how we can. First thing is that till now I talked about only condensation and evaporation. No this collision and coalescence were not done. So we have to do this collision and coalescence later on. Then again I come back, this linking can be done. So how to do the linking of LES and DNS? There are different ways. So we have to go discuss with the LES expert who developed the LES. So one approach I wrote that maybe we can do the different LES for a different DNS for the different person, and then we can do the parameterization for the mixing. Or another part we can do the, like since it is a rising parcel, we can calculate the entrainment rate or a particular cloud for a cloud entrainment rate. I don't know, detrainment also can be done. People have started doing the DNS for the ice particle as well in some of the places. And later on, it's if we can go further, we can even do the simulation of the mixing in the ocean surface and all. So, so this is the future work we have actually available. If somebody can, come forward to do this, and just I will take some more time. as I said that when we have the cloud turbulence, we talk about the turbulence properties. So the properties, as you know, the turbulence means some rotary motion, and then we have the high vortex, low vortex thing. We want to know how does this vortex thing, the turbulence is affecting the cloud microphysical properties. So this is the long, very old problem. In a quarter century before, 25 years before, this Raymond Shaw actually laid some foundation. He said that he considered actually 50% is the high vortex, 50% low vortex, and he did some kind of study. But then after 2 years, Ballinkord and Yao, Ballinkord is the person who started the DNS, 3D DNS in McGill in 2001. They said, no, we cannot say that this is the properties of the cloud microphysical property in the turbulence. They did not agree. But from 2000 to 2019, there was no work has been done. In 2019, I had a discussion with Professor Yao, sitting. Then he said that we have done some theoretical things, some 2D things. Can we do this thing in the DNS? So we actually thought, okay, we can take our DNS data. We can talk about how this is happening. So we applied different techniques. So one to segregate this data in the high and low vortex region, we decided what is the high, what is the low. And we found that finally that it is only 2% the high vortex region. It was a really very good study, and Raymond Shaw and all, they were really happy to see this kind of things after 20 years. Okay, so this work is done, and we have done a lot of study here, and it is published in the ACP, and how the things are changing, the low and high velocity, number density, mean radii, and different kind of this one mean radii and the fluctuations, everything we have done in this paper, and this is actually published already. Now what we are trying to do, this everything, all these k-mean algorithms and all, we have put into the traditional HPC. Next step, we are trying to do the same thing, can we do into the quantum computer? Because all this very complex. Like sir is saying, did you do the
computer?
We are trying to do, that's what, whatever available at the research level.
Now you conclude. Photo also has been taken.
So some IBM labs are available. Only 32 qubits available right now. So we are trying to do. So we have done this SVM quantum SVM algorithm, support vector machine on the quantum computer. We are now trying to do this one k-mean also on the quantum computing. So this work is actually done by being done by one of the PhD student in the BJTI. So we are still trying to do, and it's the good thing is that in the qubits, it's not a 0-1 kind of digital things what we do in the currently in the HPC traditional, but there we go into power 2 to the power 4 or like that. So data representation is more there. Okay, so there are many people involved in this work in the last 10 years.
Any questions?
Bipin, you said the inorganics as compared to inorganics, the mixed
we got
aerosols activated faster. So what kind of mixture? What fraction is the inorganics and what fraction is organics?
that I found this is a 50-50 we took it.
Okay.
The mixture, this table I have, I can show you.
How is physically feasible that inorganics should have activated earlier than?
That's still we don't know. That's what we want to know from the
Is it a model problem or is it a model?
No, we just did a numerical distribution here, that pure organic, mixture, pure inorganic, organic also two different types of within lower kappa and higher kappa. So all these things theoretically we are doing right now. So that's why we want to take observation either KIPEX or this to see that whether it is possible. Are you observing this?
They got confused. So you told domains depends on the domain size. If you change the domain size, mixing will change. Something like that.
Yeah, size is changing.
It's changing.
Yeah.
But earlier you said that whether you go with the KIPEX data, maybe, so the aircraft, or you take a model, you are able to get it. So these two are kind of
KIPEX comparison, we did just a fixed domain. Suppose 1 meter cube domain.
1 meter cube.
1 meter cube domain.
But then the KIPEX, that the aircraft is.
But in the KIPEX data also they calculated the same way. They are also taking the one the small cube,
Yeah.
I mean 1 centimeter cube or 10. So the
So that says
The
that
way-
it is independent of domain size.
no, it's not independent of the domain size.
So first result you are telling whether it is capex data or model, domain doesn't matter. Then,
No,
then-
domain matters. Sir.
Then,
Domain
then
matters.
you next still you are telling domain matters. So these two statements I'm kind of
No, I'm not saying that domain doesn't matter. Domain always matters. We took some small domain here. We took some data from whatever the object. We just wanted to compare because the flight is going here to here. So how we will see the data? Just we want to see the data, this data, and after some time how the data is going.
Domain is changing, no? You are changing from one portion to another. You are changing the domain, but you are using a fixed domain.
So are you
No.
trying to say that, I mean, the total domain size or the resolution? What matters?
Total domain size matters what we have studied.
So in this Kypex case, your total domain size is fixed.
domain size is fixed, yes.
So what he has done basically,
How
to say some seconds to some seconds, okay, the flight movement equivalent distance, okay. So that distance he takes as his DNS domain, and he then compares.
Actually, this concept came because how this Sudarshan is or other these Kypex people, how they are calculating the size distribution and size spectra in the Kypex data. Same way we wanted to calculate in the DNS, just to for compare. That's why this strategy we have adopted.
Anupam.
Okay. Thank you, Bipin, for nice talk. But I'm also agree with the director sir what sir is telling that the scale of what you are talking. So similar thing I have also observed. I mean the real DNS and scalar DNS. So your result almost similar. So there is not that much change also.
Results are similar.
So whatever you have shown the PKE, that if you have compared the
Yeah, energy
DNS
spectra I
and scalar.
compared.
So
Yes, yes.
point is that what Bhuda sir is also telling that what it is that when you are scaling up means the resolution you are increasing or domain you are increasing.
Domain.
So number of droplets is increasing, right? Yeah. So that means the growth what you are getting or activation of number that is actually changing, and then it actually impact on the spectrum, drop size spectrum. Am I right?
Once we are going to the scaled up, we are talking about the super droplets. So the total number of droplets we consider based on the multiplicity.
Right.
And how to calculate any microphysical property, then we have to consider the multiplicity. Okay.
Right. So then question is whether this resolution or scale is important or not. Or
No,
if important, how much it is important. So that is still I'm
The
also
scale is there. We have to work up to the Kolmogorov scale. That is always fixed. That's why it is called the direct numerical simulation. We are not going compromising with the scales. So we are coming up to the Kolmogorov scale. Okay. But the Kolmogorov scale is changing when we do some kind of scaling of this viscosity. That is the.
that's okay, but I'm talking about the process. Suppose you are changing. So how much it impact on the growth process? Because you are showing the spectra. You are all dealing with the spectra.
No, we have done the. You are saying that the microphysical property how it is changing.
Yes,
I have shown
when you
only.
are comparing with Kypex.
Yeah, no, the Kypex is real DNS. Yes, with that is nothing.
That's right. So Kypex, you are comparing the droplet spectra with your DNS spectra. So it is matching. So that means that which one important? Your scale is important or this one important? So that was actually I'm
Yeah, I got the point. So actually,
Yeah, that is the point.
yes.
So you are telling your model is showing all the data. Then you are telling again it depends on domain.
Exactly.
These two are and anybody will get confused.
Exactly.
No.
Why it should depend on domain?
It should depend on the domain, because if you really want to study how the turbulence are changing and all, but the Kypex is, I told this, so maybe the Kypex people tell how they are calculating the data. I said that we wanted to calculate.
That actually the droplet is number is changing. So number if you change, the growth will be changed. So that actually is the main factor. What I feel, I'm not sure, but
No, growth equation we have to take care. I told
that's
you.
why. That's why
Growth equation we have to take care.
changing the scale means domain size.
Uh-huh.
Not, so then your number of droplets. So if NC is changing, so then the deposition growth what you are in your polar equation that will change. So that means basically it impacts on your spectra of the droplets. So that's why you are getting this. What I guess, I'm not sure. Maybe in your experiment.
No, if it is the, I mean, I'm saying that the confusion comes how the Kypex data is calculated. So I told this strategy we have applied because the Kypex data, when they are calculating the size of sector, they have this kind of study. So I don't know, maybe this Sudharshan can tell how they are calculating. How they are calculating the same way, because when we compare, we have to have the same way how you are calculating size of sector in that flight data, how we should calculate from my DNS data. That is what we did. But that we took the small area from this probe, whatever they have put into the data cloud. So there we are not comparing the size, total size. We are just comparing a small data or a small DNS data. That's what we did.
Good. Actually, see, you gave a lecture almost 10 years back, no? Before joining IITM, and now you're 23. That's why this confusion. In between, you should give some.
Sir, you give me an opportunity, I will.
The opportunity always there. All is there. Mic is there. Camera is there. You just tell, I'll give lecture. And you know, anyway, it's good.
Yeah.
And you have also advertised nicely. You need postdoc and students, so I called students. Okay. And you also gave the Louis Thomas. I'm wondering what Louis will now tell in her PhD. Dissertation seminar. Almost everything you have covered.
No. But anyway, I have covered so many things.
But anyway,
one part is this.
But now, the last concluding remark, Bipin, that because this DNS is a hugely expensive, and you have shown 2.7 terabyte funnies.
No, that was never
a huge computer HPCs. We are struggling.